Yeah, great. Well, hi all. I've prepared a talk that's largely without, well, I think it's actually entirely without equations, because I personally hate learning maths from a board in equation form. So if you need something defined more precisely, just ask me. And because these chalkboards are awesome. And if any of you haven't used the chalkboards, try them out. They're just fantastic. So here's the 300 slides are spread among 4 main topics. I've got the looking at the embedded graphs and basically why I care about them. These are specifically my embedded graphs, because everybody's got their own embedded graph, just a graph structure embedded in space in some way. But there's some that I particularly that I was interested in, so I'll give you a look at them. And I was looking at them, I was trying to analyze them in terms of knots and links, just trying to analyze the entanglement, the spatial complexity of links, and it turns out that's a fairly inadequate measure, or incomplete at least. I discovered these things are called rattles, which turns out have been discovered plenty of times before, but I'm sticking with my name because there's no other better name out there. Developed them into these more complex beasts that are really kind of odd. And then at the end, I've got this bit of a discussion about entanglement as a whole and the place of ravels in that pantheon. So first of all, the story started with EpiNet, which is a project hosted at the Australian National University, which is where I did my PhD, and stands for Euclidean Patterns in Non-Euclidean Tilings. So the pictures say most of it. We've got here we've got a Poincare disk representation of the hyperbolic plane. We've got a tiling in it. This one just happens to be alternate hexagons and squares, and you can wrap this onto a triply periodic minimal surface. So we take a chunk out about the middle, it's a chunk about like so, typically a dodecagon, 12-12 tiling of a dodecagon. Pull that out and just wrap it into space, and the minimal surface has negative Gaussian curvature, so it's all happy, and it all just works. And this is a way of generating structures in space, periodic structures in space, from two-dimensional tilings. And because 3D networks are such a pain to analyze in general, that being able to play around with them in 2D is often worth the sacrifice of having to do this method. So you've got a 2D tiling, gives you a 3D structure. So here's, for example, I've just picked the same one, wrapped onto these are the genus 3 minimal surfaces, the simplest ones, the most symmetric ones, the ones that are most likely to turn up in chemistry actually, because we've got a big sort of chemistry focus there, applied maths applied to chemistry. So wrapped onto the primitive, the gyroid, and the diamond, and different wrappings give you different structures in space. So this is my background. Now, the standard way to do that is to map this dodecagon here. Map these 96 what they call flags in tiling theory, just these little triangles. All these triangles are identical. Obviously, the size thing is just an artifact of the Poincare disk. So we've got a group theoretic approach that describes how one wraps this onto those. You can look at this paper any paper by Vanessa, one of my PhD supervisors, will give you a good look at that if you want to investigate it. But when you're doing this, you can really we just chose the simplest, easiest, most symmetric way of wrapping this kind of dodecagon onto our shapes to generate tilings. But then some collaborators, mostly in Italy, Davide Proserpio is the key one, is they started discovering chemical structures that are much like the ones we're generating, but with entanglement in it, with interpenetrating loops. They call it self-catenating, and these kind of other structures. And so that was the challenge there. How do we go about generating them? And one way is to put a really, really nasty tiling on top of this, and then after you follow our standard map, you'll end up with a nasty enough network that it's guaranteed to have loops. But that's obviously fairly inelegant, and you lose the main benefit of doing the analysis in 2D. So instead, we wanted to look at the different ways of mapping a different dodecagon, for example, onto these shapes. So putting a shear into it or a twist, and so any tiling you put on there will be twisted as it's wrapped onto the structures, and that twist will then later manifest as some kind of entanglement. So there are a host of technical difficulties that I won't bore you with. And so we started off just looking at the torus because the universal cover of the torus is the Euclidean plane. So you've got all kinds of things like the parallel lines keep going equidistantly, really fun stuff like that. And math is just much, much easier. So you take a torus, chop it up. I mean, you guys should be fairly familiar with all this gear. And so we're looking at tiling the torus with some simple familiar shapes and seeing what we could do to mess it up to generate tangled structures. So what I would do is just combinatorically is we're looking at the tetrahedron here. So K4, we've got, you can see the vertices are marked there, A, B, C, and D. And locally, because it's K4, you can see that A connects to B, to C, and to D. And so this little circle here that comes out fairly terribly on this projector is like a local surface patch. So we know we're going to want to stick it into a torus. And so we can just basically define these surface patches and stick them together the only way they go. And we can generate different tilings by permuting the order of which the edges come out. And so this is, if you have this particular set of surface patches, then this is the only way they go together. And so you see it generates this tiling with 2 octagons and a square, which has a million different names in different areas. So I won't try and guess the name you guys know it under. And then you can take any unit cell of unit, a translational unit cell of unit area. So here I've picked one with these vectors 0, 1 along this side and 1, 1 along that side, and rectify it back into a rectangle and just wrap it on. So this is like what I was saying before. So instead of either you can just take this shape and wrap it onto a torus, or you can rectify it first. I mean, it's just semantics there. And that gives you these kind of structures. Now, I hope it's been up long enough for you to notice that there's something a bit weird about them, insofar as they contain knots. So it's the same structure, just different renderings, and they contain a trefoil knot. So this is a proof of concept that we can generate interesting structures by doing this method. So here's the trefoil knot. So this was just traced from that with, gosh, this projector's not crash hot. You can see if you just omit AD and BC, these 2 shorter lines here, you've got a trefoil knot staring at you. So this is the kind of, this is a demonstration of the existence of knots within. Now the tetrahedron is small enough, K4, there's no disjoint cycles, so you can't have any links, any multi-component entanglements. So they were not on the table, but as you look at more exciting things, you start to see knots and links appearing. And of course, because they're on the surface of a torus, they're torus knots and torus links, which is just, natural. So here, starting to look at entanglement and trying to analyze the entanglement. These are 2 different tilings in the universal cover. On the right, we have one that's made of, around 3 of the vertex, there's 3 9-gons meeting, and one of the, the one on the right is the tiling with 9 gons and triangles. One on the left is with octagons and squares. And you can see on there on the right that this trefoil, there's actually 2 trefoils present, one in a 3 cycle, so from A through to D, around through to either C, B, A, or just through C, A. So there's a 4 cycle of K4 or a 3 cycle, both of which are knotted. So just saying that contains a, so I'd say the one on the right contains 2 knots, but they're obviously fairly closely related. But just to give you a soft introduction into trying to analyze the entanglement that's present. So here's a cube, because we all like cubes, they're such a familiar shape. There's one of the tilings, there's several that tilings of the universal cover that'll generate cubes. And just choosing slightly different unit cell shapes gives us this variety of different entangled cubes across the bottom. Now if you have a look, you can see that one on the right is, this one, for example, contains the Solomon seal link, and that's the 2-1 homotopy. There's a Hopf link right here. There's, you can see on the right, there's fairly clearly traced out, there's a high homotopy knot, or at least I think it's a 3-4 homotopy. And so you can see just by shearing a unit cell, you put more complexity, more twist into your structure, and you get more more action back out.
So you just gave us proof that these four are different.
Yes, quite.
Embedding in 3 spaces.
Absolutely, they're different because they contain different graph minors. Yep. Now, here's a table of these lowest energy because it's relevant to chemists. Chemists actually make these things out of little blobs of, I've forgotten what they call them. So that we invented an energy function, which I don't think much of, but there it is. And you can see here's a list of the simplest ones, analysed partially in terms of the knots they contain, where this notation 4 times 3,2 just means it contains 4 trefoil knots. And these numbers are the homotopy types of the knots inside. And obviously the same for the links. So we're seeing a bunch of 2,2, 4,2, and 6,2 links, depending on just how you shear them and the combination. Now, this seemed well and good to us. We were fairly confident that we had a good handle on identifying the complexity of the stuff we build in this way. Except, sorry, I missed my tangent. And so we take this stuff and then, and so we felt happy about this stuff. Now, just to finish the story, a very slight tangent before I come back to the main journey, is that this was mostly MIF stuff. She was a PhD student at the same time as me, and she just took my ideas and solved the technical barriers, and worked out it was actually easier just to have a nice tiling of H2. In this case, they're trees, but that's just infinite tilings, infinitely sized tiles, and just give it the appropriate shear. Turned out to be technically easier than moving around the dodecagon, as I said, but it's the same idea. And so she takes a bunch of structures, different infinite tilings like this, and wraps them onto the P, the D, and the G, the primitive diamond and gyroid surfaces. And she gets out really cool structures, as you might expect, and with lots of relevance to biological systems and stuff. It seems that for whatever reason, biology likes minimal surfaces, and it likes. And so some of these structures, I think actually this one is a good candidate for how keratin fibers assemble in your skin. So who knows how or why, but it's the best that the dermatologists have right now. So in the analysis of entanglement, we're happy with the knots and the links, but there are other measures too. Which you should be able to tell by my tone of voice, I don't think much of. There's the minimum crossing number of a planar embedding. This is a really standard measure from knot theory, and so just apply it to a graph. But for a large graph, you've got to keep in mind graphs are so much more complicated than knots, because a knot is just a simple cycle and a graph is a composition, a whole bunch of cycles stuck together. And so the combinatorics of how you can do all this stuff is just huge. There's also graph embedding polynomials, which are great. They're a really powerful measure, but they're not really human interpretable, and nor are they unique to a particular graph. We've got other geometric measures, so you can like fatten up the edges until it sort of gets as puffed up as it can get, and that's a measure of its energy. You can minimize energy other ways. You can imagine that each line segment is emitting light in all directions, and you measure how much of that light that the graph captures, how much it self-illuminates. That's another measure from knot theory. There's all these kind of things. I don't think much of them in this context. I mean, but they are potentially useful in a different context. So having analyzed all this stuff in terms of the knots and the links, what about these guys? So those of you familiar with Thurston's book might remember the tripus, as he calls it, or the knotted Y. That's there in the top right corner. Kinoshita published this in '72 in the Pacific Journal of Mathematics. So this is a theta graph, 2 vertices connected by 3 edges, hooked up together. Now, as it happens, people have been making rope since I think 3,000-4,000 years. They have exhibits in Mesoamerica, and so they make it more or less the same way as we used to. This old school three-ply rope. And when you splice a rope, the really obvious way to put an end on a rope to stop it fraying, you're making this exact same structure. So if you just ignore the body of the rope and look at this here, you've got the same structure. Now, this is a bit challenging because it doesn't contain any knots or any links. So I've got a demonstration for you, one I made earlier. So here we have this, whoops, I'll try and keep the symmetry, but it's hard. So here's this structure you're looking at here, and I'll just close it up at a second vertex. And keep in mind this has threefold symmetry. Every edge, this is just this guy or this guy, well, they're all the same. So it's pick your favorite image, and that's what this is. So knots and links exist in cycles. This is a theta graph, so there's no disjoint cycles. So there can't be any links in this. And a knot would exist in two of the edges, and hence not the third. So keeping in mind that they're symmetric, I'll just remove this red one, while carefully not changing the other magnets behind your back. And you can see that untangled. So there's, thank you all. So you can see that there's mathematical proof to know, but they're rather more dull. So this is the kind of structure that began to plague us, because it was fairly obvious this couldn't exist on the torus, although obvious isn't the same as proved, until last year actually, when a PhD student of Dorothy Buck's at Imperial College named Senya Bartel spent her PhD thesis proving that these kind of things can't live on the torus. So it turns out our analysis of tori, of entanglements embedded on a torus, is still okay. But it was a bit of a wake-up call, because as soon as we step up to more complex handle bodies that we're putting our tiling on, or our lines on, then there's the potential to have more and more complex structures come out. In fact, there was this guy, Frederick Norwood from the East Tennessee State University, who in 90-something, he was looking at the knots that embed on a two-handled torus, and found that looking at these guys, he found, I think, all but one of the 7 crossing knots. So when
you say about a torus, you mean an unknotted torus?
Yes, an unknotted, quite the standard configuration, just yes, an unknotted torus. So and so there's a real proxy here of that the more holes something has in it, or the more bridges from one place to another, the more complexity this handle body can sustain. So these kind of things read their ugly, beautiful heads. I'm not sure. So yes, so on to part 2 of my 300 slides, and the existence of non-knot and non-link entanglement modes, so ravels, as I insist on calling them. Now, obviously, any number of edges can be involved. This is just the most symmetric versions. There's a stack of ways of doing this, as you can probably imagine. Combinatorically, there's a vast number of changes you can make to this that don't introduce a knot or a link. So these are just the most symmetric examples. And I call them vertex ravels. Now at the start we called them ravels more generally, but then I found something that has exactly the same, really generalizes their properties. And so I figured they deserve the name ravels. And so these were demoted to the status of vertex ravels. Now, we want to call them ravels, of course, because when you remove one edge, they unravel. So, oops, sorry. Got my slides out of order. I'll come back to that. Now, Erica Flappin picked up on this ravel business when we published it in a chemistry journal, because they have actually found ravels inside chemical structures. And she's got her definition, which is nice that she phrased it in these math terms, given we provided it for chemists. But it's slightly wrong in a number of ways. For example, ravel is spelled with only one L, the American way. That's one of the most egregious aesthetic errors. But there's also a larger problem. And that problem is that this issue of selective ravels, right? So this is quite a big deal later. So here we've got 2 trefoil knots. This is, you can just, if you want to just look at one half, it's just a trefoil knot with a vertex whacked on, and then the vertices are merged. Now, if you hook them up this way, as per in the case of B, you can see we've got a ravel. So this is a petal graph. It's a one vertex, two edges coming off that loop back to it. And you can see here that there's no knots, there's no links. It's fairly easy to see. I mean, here there's no possibility of any links because there's no disjoint cycles. This cycle here certainly isn't knotted, and nor is this one. I mean, it's just got two flips in it. So you can see that's quite happy as a raveled vertex. The one on the right obviously is not. It's this case because these two edges can join up. You've got knots present. So this becomes a big deal because these dotted lines don't have to represent just the edges joining up. They can represent the entire rest of a graph, of a much larger graph that this is embedded into. So and so then you have to worry about the connectivity elsewhere in the graph to define the local entanglement present around a vertex, which is kind of odd to my mind. Yeah, maybe a few confused faces, but we'll come back to that. Yeah, so and these kind of vertices that separate a graph into different components are known as cut points typically. Bridge vertices, all kinds of different names. And that's when this is actually an issue, when the two sides of the graph don't talk to each other, aren't connected, and so you actually have the potential for this distinction. So here's a really ugly definition. I encourage you not to look at it, just because every time I was trying to, because they're sneaky enough that I haven't worked out how to concisely define them is the real problem. But to give you one version is to say that if we have a vertex, I'll just make it a 3-valent vertex, then you have a ravel. One way to insert a ravel is to define a ball around it, excise the ball, play with the edges to your heart's content, and then stick the ball back with the edges exiting in exactly the same place as they used to, and then that will be guaranteed to give you a vertex ravel as long as you, with the playing with the edges, you haven't introduced any new knots. So here's one I prepared earlier because they can be fiddly to draw in front of 40-ish people. So here's just the same picture you've been seeing, but we've got the same idea. We've got the ball. We've taken the edges leaving our central vertex. We've twisted them around each other, raveled them, and stick it back in, and that's going to be a vertex ravel. I can try and give you a better definition. Well, I mean, there's a number of bad definitions I can give you, but I hope you get the picture. So in terms of analyzing looking at an embedded graph, trying to find their existence, that's different definitions are more useful than others, which is this one's I think a rather constructive definition. Vertex ravels, of course, you can put them in shells. I mean, there's many things. This is just one feature I picked out. You know, you can ravel a vertex, and then you can just choose to another slightly smaller ball. Here I'll draw it solid. And now we just re-ravel this inside bit, and so you can have multiple layers of different sort of vertex ravels present around a single point. So that's just one feature. I mean, there's many others, but you can see that you can just repeat this infinitely to have an arbitrarily complicated entanglement just there, localized without the knots and links.
Can you have a ravel and then in another shell unravel it?
No.
You can't do that.
No, you can't. There's even a proof of that, but again, I'll skip it. Oh, it's a pain in the ass. I don't know actually. I've read it with glazed eyes. There's certain aspects of knot theory proofs that I just don't get on well with, and this was one of them. You know, there are certain really elegant and beautiful knot theory proofs, and there are others that less so. Okay, so now on to, I guess I'll just justify the name of ravel here. And I remind you of this kind of quality of them. We call them ravels because as soon as you damage them, they unravel. So we've got a vertex ravel here, and we removed one of the edges, and it just straightens out. That's in fact what I showed you with this toy. You know, we had a ravel, removed one of the edges, and it straightened out. It's really Borromean rings, Brownian links. really, really similar property, both conceptually and also in a slightly deeper way. If you look at, again, Thurston's book, about the same place that the tripus appears in the 5 pages either side. So yes, that's the reason why I persist in calling them ravels, because it does seem to me, at least, to be a reasonably elegant name that captures their character. And just to habituate your eyes to them, here's a bunch of ravels. We've got a petal graph, 3 lobes going off one central vertex. Top right, we've got a tetrahedron with it's this cycle is just a boring cycle, and this vertex, which should be like the top of the pyramid, it's got a ravel around it. Another petal graph in the lower right, and here's just a familiar theta graph. And it raises the question, of course, which vertex is raveled, because you can imagine grabbing one of these and pulling the edges out in a nice straight, untangled way, and then the ravel is centered around the other vertex. And of course, you just reverse that, so you can flip back and forth where the entanglement is centered. That's more or less just like inverting space, in terms of your ball, change the inside or the outside. So not really a big deal, but just a small thing. So we're up to slide 200 already. Complex ravels and their properties. So I'll come back to this picture and explain it more, but you can see that they do start to get a bit more complicated and more widespread, not just stuck to a small ball around a vertex. Where I should mention the bit that I forgot. In this ball construction, the ball is allowed to have a maximum of if it's an n-valent ball, it has only the edges that are going to the outside world penetrate the ball, intersect with the ball. So you can't have extra edges from the outside looping in and getting in the way, doing this kind of thing, because as soon as you got that, you got the potential for a link to exist. So previously, if that edge has been here, we've got no link, and now there's a real chance that if you allow this kind of thing, that that there could be a link in, for example, in let's say either of these cycles. In between those 2 cycles, so we've just created a link. So the ball was exclusive of the rest of the graph. So wandering ravels. Here we've got this idea. It's easier probably to start at the right, actually. We've got a standard vertex. We grab one of the edges, bring it around to the other, lock it in. You guys have probably done this playing with rubber bands when you're bored on the phone or something. And so of course these are ambient isotopic, this sequence here, and the difference is where this red loop finally loops around and locks onto the blue one there. And there of course we have a vertex ravel. So this vertex ravel is actually one of those shelled ravels I showed you. So it's the simplest ravel, and then it's an antimeric partner. It's the partner with the opposite chirality. Yes, so that's A. Yes, simplest. This kind of ravel, it can look like so. On the right, we have 2 other versions. We've got this kind of lariat version on the right-hand side, and these I started making them up really. I mean, you can link any way that you can take an edge, wrap it around another edge without inducing a knot or a link. Will be a valid mechanism for one of these ravels. This one's kind of interesting though. It'll pop its head up later. And the lasso one is just for fun. So wandering ravels. They're an extension of these vertex ravels, and they can travel through space. So here we've got a mistake. Okay, now here we've got next slide, a tetrahedral graph, just as the graph structure, and here's a wandering ravel that you can see there's no way to define a ball that excludes this blue line that would contain all the business part of what's going on. So I've just redrawn this to put the complexity elsewhere to make it more visually easier to follow. And this is just a cycle analysis where this is all the 3 cycles, and at the bottom we've got all the 4 cycles. And just by looking at this, I hope you can persuade yourself that, in fact, all of these loops just retract back and straighten out. So this loop will go back to being straight, and it'll lose its hold on this guy, and this guy will straighten out, and so on and so on. So you can see just this is a visual proof that this particular example I chose doesn't contain any knots or links.
But you can prove that you can unravel the ravel.
Yes, there is no anti-ravel in the same sense there's no anti-knot, if that's what you're asking. But also, this is certainly an entanglement. Yes, absolutely. Yeah, so this is kind of straight. Now notice there's this domino effect that one links to the next, to the next, to the next, and typically they have to go around in a circle. So there's the last one has to link in that actually provides the entanglement, because up until that point, just as you saw a few slides ago, there was no entanglement. So so this kind of domino effect, if you just break one edge, release one edge, then brrr, just like when you're playing with the rubber bands, and they all just sequentially undo, you're going to have exactly the same behavior occurring. So again, that's why I call this a ravel, because it's got the same unraveling behavior, it's got the same sort of Borromean, Brunnian character. And the wandering ravel, of course, because it can move around in the network. So here's a picture of it sort of starting to move around. Same old motif you've just seen a bunch of times. Here I've put it around 2 vertices, and you can see in B it's more of the same, but this extra edge that comes in from the outside, this could be anywhere. You could have picked an edge that's geometrically on the opposite side of the graph, or topologically, however you want, grab it, pull it over, so you've grabbed it and you've got it sort of doubled up in your hand, and as you weave it through the graph to get to its location, you don't introduce any knots or links, because of course it's doubled up, so anything that links will unlink, and you're not introducing any knots, and bring it and do this. So you can see that this kind of, that you're really defining this kind of path of entanglement, which is the sort of the domino path that if you release one, then they sequentially undo all the way back around. Now, well, you notice I've got 2 anchors there, which are fairly important. So here's a visual guide to their importance. Is that here if we have this is the same old motif, but here I've taken like a 4-valent vertex and split it into 2 3-valent vertices, joined by this little green line, and you can see that having done this, presuming that there's some kind of graph closure between vertices A and E and B and F, that we've got this red cycle and the blue cycle, and they're clearly interlinked. I haven't proven this one, but I'm sure it could be done. This is just a link. But were you to contract C and D, then of course you prevent the disjoint cycles from existing, so you rule out the existence of links right from the start. So, so I call these an anchor. And now an anchor is a vertex that's, whose edges are involved in the wandering ravel, and there have to be at least 3 edges leaving a vertex that are involved in the wandering ravel. And this is enough to be sure that to prevent these links from forming. That's which is the really sort of big task in a constructive way when you're building these. It's easy to avoid knots, but avoiding links is the big deal. But if you've got one of these as part of your wandering ravel, there can't be any links. Because keep in mind that as soon as you sever one of the edges, the whole thing undoes sequentially backwards. And so because we have 3 edges meeting at a vertex, or at least 3, then any cycle, this vertex can belong to at most 1 cycle, and that means at least 1 edge gets left out of your link analysis. And so anytime you do a link analysis that involves a cycle going through that point, you're not going to see the entanglement, because you've dropped the other edges, because they can't be part of disjoint cycles. So that's the role of these anchors here. So here's some I've just decorated a cubic lattice, and you can see this fella is these little red numbers are just the number of edges that get involved with this wandering ravel, and you can see this guy's got 2 anchors, and so in fact is a ravel. But here, it's not a ravel because we've got a link. And it's really easy to persuade yourself of this. So in hindsight, I should have highlighted it for you. But really, you can just pick an edge coming in and back out and just find any other one that goes through it. So my apologies, I didn't highlight it for you, but it's if I give you time, it's very, very easy to persuade yourself that there are links present. So more generally, this is that was a very specific a square lattice. But here I've really tried to gather that abstraction I was talking about when I say an edge can come in from a far distant place. So here we've got just an example where these endpoints are just meant to represent two endpoints of an embedded graph. They could be any edge anywhere in the graph. And then you just grab that edge and you pull it through the graph. It's doubled up in your hand, weaving through, so you're not doing any of the bad stuff, no links, no knots. And then you pull the loop through. So I started with this orange one. And then the blue one, for example, this sky blue one, I poke it through and that locks the orange in place. And these can be from anywhere, geometrically, within your graph. And so we're introducing this path of this tube, essentially. You can define a tube around this that contains all this entanglement that you're bringing in. And of course, as soon as you snip it, break just one of these, and they're all going to retract back. That's what these little arrows are, the direction of retraction. If this, what color do you guys call that? Let's call it salmon. If this guy vanishes, is cut, the red guy, lasso, pops off, retracts back, the gray retracts, the blue retracts, and so on, just like dominoes. Again, this is just this raveling characteristic. Now, we've got other ones called polytropic ravels. Now, this is the one I showed you before. It was next to the lasso, and I said there was a point to it. So that's this kind of link whose name I didn't write down because I knew I wouldn't forget it. And now, of course, I've forgotten it. But it's this link. It's as many components as you want and just wraps it around in a circle. Again, you can do this exact same thing with rubber bands. Now, one of the cool things about this is that you can do this kind of motif. You can join them. Here, I've just shown you a way to join three. Just by choosing two adjacent points and make them the endpoints of the edge, hook them into the graph as you see fit, and so you can construct this kind of graph around. You can construct this kind of graph, this kind of entanglement anywhere through your graph, just like before. But this one's cooler, much cooler, because you can anchor it at either end. Here's this, this black bar just representing something it locks off on. So if you're going to snip this middle one, you'll see that immediately releases this green one here. There's nothing holding it in place, and so it'll flip back through, and just like the domino effect, it'll continue on. Meanwhile, it'll also continue to the right. This burgundy one, this inner loop here, you can see it'll be released and plop through, and then it'll release, and so on along the through the network. If one of these guys fails, let's say we lose the red fella, these two green loops here can just retract straight back through, releasing the yellow. Everything falls apart. So what we've got here is something that's really kind of odd. It's an entanglement motif present in a graph that actually has the same properties of a graph embedding. So it's like this tube I spoke of running through the network. Well, this tube can now branch, and as soon as you destroy one part, everything else goes. Just dominoes in every direction. So every connected component of this entanglement just gets lost. So we've got vertices, we've got junctions, we've got tubes. So really we have all the properties of a graph, except they're applied to a kind of entanglement motif present within a graph embedding, which I think is really weird. So anyway, I've used that to make this picture, and I wished I could make something more complex, but it gets so hard keeping track of everything and not accidentally making a mistake and bringing in a link. So that, for example, is one of these polytropic ravels. So we've got here's a vertex. We have 3 different strands leaving this sort of meta vertex. It goes off, and here we've got, like, for example, a 2-valent vertex, however you want to look at it, and runs off there. And again, we've got the same property in each of these cases. So in graph terms, there's something just like so, except, of course, I've tied that graph into a vertex ravel. That's why it's so squiggly and all over the place. That if you have very bad vision and you can just see these sort of blurry lines, I'm hoping it looks something, whoops, more or less like this. Well, it should look identical to that. So here's just an example of this weird property that I can't explain, but I do like. Moving on to slide about 398 or 298. No.
Can you go back?
Yeah, sure.
So, what about twists in those strings?
No issue at all.
Because
Because you're not introducing any linking, you're not introducing any knots, so they're out, so it's still a ravel. No, the graph is maintained, and obviously there's a property to do with the number of. Obviously, you could somehow annotate this graph according to the number of twists present, but just because there are twists present isn't going to change the fact that if one end gets released, it's going to propagate. It's all going to come undone. It's just going to untwist. So, yes, it'll be a different entanglement, but still within this rubric. Okay. Polytropic. Polytropic, no, I didn't, and the definition is that it's just one of these entanglements which releases in both directions, or in every direction. That if any one component fails, that the every linked edge is then released. Every edge with which that particular edge is linked is entangled, that gets released, and that propagates through. So that's what gives you this real graph property. Whereas, of course, the wandering ravels were just a cycle. A cycle that could travel anywhere through the graph, but only a cycle. And I got this, by the way, because I'm a really keen rock climber. And if you look at the topology of this is precisely how not to set up your anchoring gear. Because if any one component fails, you die. So that's, in fact, how I came up with this idea. Now, planarity. What's all this business about? So here's this definition I didn't like. Oh no, here's a definition 1.2. It was me trying to sort of repair their initial definition, but without a lot of success. That's why I left it out earlier. But it's all about this non-planar business. So the non-planar part is, in a lot of the literature looking at entanglement, there's a lot of claims by, say, in the Charlemagne and Thompson paper, if anyone knows that, or their result, or by Yingqing Wu from one of the UCs, Santa Barbara, I think. There's a lot of discussion about a planar a graph embedding is planar if the graph is abstractly planar, that is, if there exists a planar embedding. So if it's an abstractly planar graph, and if the embedding has a number of other properties, you have an entanglement, is the basic idea here, at least within abstractly planar graphs, because the other ones are sort of forced into it. So the way I look at that is that I say if there's a graph embedding, like a tetrahedron cube I showed you at the start, that contains a knot, then intrinsically we've got issues with crossings in the plane. So I say I'm a very blaming person in this kind of context, a blameful person, as your old president said. And so you take these, I say that knot is responsible for the entanglement. That knot is responsible for the non-planarity of the embedding, and thus it's so that I guess the shift I'm trying to articulate now is to actually identify various entanglement motifs within an embedded graph that contribute to the embedding, and not just waving your hands and saying this is planar embeddable, this is not planar embeddable, but saying this is planar embeddable because it has certain features as described by various mathematicians in various papers, or it's not because there's a knot there, or there's a ravel there, or there's a link there. So what I really want to do, and this is a work very much in progress, is to build a taxonomy of entanglement motifs that you can point to and say it's that presence, however kind of nebulous or spread around the graph, that prevents the planar embedding, that is responsible for the entanglement. So that's the direction I'm coming from, and like I say, this is a work in progress, so you might hear some fairly dubious logic in the next few slides. Especially because it's a really fraught area. There's a lot of difficulty here. A lot of graphs don't have an untangled embedding. K6, for example, any embedding of that into space is going to contain at least a hop link. That's, I think, Erica Flappin proved that a while ago. And K7, I think, contains a trefoil and a bunch of links, because of course it contains a whole set of K6s. Even if you look at like a cubic lattice, just joining the integer points in 3 dimensions, if you choose a big enough chunk of that, then you can actually just define a kind of coarse-grained trefoil. Think of a trefoil in space on a big scale, and then just locate it to its nearest vertex, and just join up the edges, and you've got like a trefoil in space present inside just a cubic block, which is obviously ridiculous, but nonetheless it's there. It's just a question of how you want to analyze it. And so these ideas get fairly complicated fairly quickly. Also do with the selective graphs that I mentioned before. My main problem with Flappin's definition was that it didn't address the role of selectivity. So what happens if you have a graph? Let me see. What's the best way to articulate this? So in just the cases before, you had the selective ravels that, sorry, brain fart, that get stuck together, and really the graph closure becomes super important. So let's say you've got yourself a nice raveled graph. I'll just jump back a whole bunch of slides. Oh gosh, here we go. So if we've got this kind of situation where we're living in a happily raveled world, we've got some big graph off there and big graph off there, and then someone comes along, just adds one single extra edge, joining the two up, and all of a sudden causing problems for us. Or it might take 2 edges because of the whole link thing. In any case, you've got basically an embedded graph. You do a really simple modification of this graph, and you lose all the raveled character, and you gain knotted character. So my project has obviously got a lot of difficulties. Oh, you saw my tree, right? Now, one of the really helpful results is one by Yingqing Wu, as I just mentioned, who discusses the fact that all obstacles to planarity, which for me means all instances of entanglement, are due to this. There's an edge that runs through a cycle. And he's only looking at planar graphs, and there's a few caveats. But fundamentally, we've got this kind of restriction. And I find this astonishing because it's so obvious. I mean, it's so intuitively graspable. But also because it's very powerful. Because if you think about a knot self-intersects. First of all, it doesn't, depending on how you're defining this disk, which varies between different proofs. So I've forgotten how he defines his disks. But if you just close up the knot, it either penetrates itself or it makes something that's not a topological disk, depending how you do it. And or else, so in the case of a knot, it self-penetrates. In the case of a link, you have other cycles penetrating. And in the case of a vertex ravel, or any kind of ravel that I showed you, there'll be that anchor vertex. And that anchor vertex will have, so the situation there is that you'll have your cycle, which must contain the anchor vertex, and then this vertex comes out and does its wrapping around business. Not sure that's exactly right. It might be, might not be. This is just a desymmetrized version of what you've seen many times before in the slides. So here we've got this situation where if these ideas can truly be extended beyond the context of planar graphs, then any entanglement is either due to a cycle intersecting itself, a cycle intersecting an edge that's a disjoint, as in far away in a topological sense, or else a cycle that intersects an edge that's connected to it at a vertex. And if you look at it, that's all the possibilities. I mean, if you look at all the edges that are present in a graph that could be this nefarious guy here, who's causing this entanglement, he's either got to be part of the cycle, not attached at all, or attached at one end. So that gives me hope that in this toolbox of of topological motifs that can be responsible for entanglement, that's actually there are only three. There's only knots, there's only knots, links, and ravels. Because of course, before we realized about the ravels, we thought, oh, there's only knots and links. And then when we did realize, it opened this Pandora's box of what else could there be. And the hope is that there's just those three. And I think that if this result does generalize, and I managed to get this done, it does generalize to a slightly more robust circumstances, that we can prove that knots, links, and ravels are in fact the only three entanglement motifs. And in any graph that contains entanglement, as in doesn't want to embed in a planar way, I should be able to point to a specific feature of that graph and say there's a knot there, there's a link there, or there's a ravel. And that can be the only things responsible for any non-planarity. Obviously, this project is not well advanced, but here's my hypothetical taxonomy of entanglement. Those of you who read The Little Prince by Antoine de Saint-Exupéry will recognize it. It's the lazy man who didn't uproot his baobabs when they were young, and now his planet is overtaken by them. But this is my taxonomy, because of course relating knots is very difficult in the same way relating the branches in here. So each individual one is quite hard to tell apart, but there are three broad classes, and only three is my hypothesis that I'm hoping to prove in the near future. These are the people I was working with, and a lot of all the second half was my work. The tangled polyhedra stuff was with Stephen and Vanessa, and the ravels was with Stephen and Miff, the Vertex Rival stuff. I'm to blame for everything else. And yes, thanks to Senya Bartel. She was the one who proved last year that, that these kind of objects can't exist on the torus, and finally put my mind to rest. Thank you.